Okay, so take two. Our final speaker for today's workshop is Kelsey Allen, who works at DeepMind, and she has a very exciting body of work that involves differentiable simulation as well as a whole bunch of other things. And she will soon be a professor at the University of British Columbia. So with that, Kelsey, feel free to take it away.
Awesome. Yeah, thank you very much for everyone for joining me and for the organizers for hosting me. I'm really sad that I can't actually be there in person, but I'm hoping to make the last talk of the day still at least a visually compelling one. So today my talk is titled Simulation from States and Sensors. And as mentioned, I'm Kelsey. I've done all of this work at Google DeepMind, and I'll be starting a lab at UBC and the Vector Institute if anyone is looking for positions. So if you haven't already been convinced of this throughout today's sessions, I will tell you that I think simulation is very useful in a variety of different settings, right? So the first is robotics, which is what brings us all here today. And robotics very heavily relies on simulators, both to actually train robot policies before they're used in the real world, right? And also simulators are used online to help robots select sequences of actions which are likely to lead to success. But simulation also comes up in these sort of robotics adjacent fields that I'm also part of. One of these is design, engineering design in particular, which also very heavily relies on simulators that have to often be extremely precise, right? And this, for example, can allow you to determine whether or not a given joint configuration is going to be robust to a very large force on each of those joints, and if not, how to rearrange them. And this ends up being critical in a variety of engineering domains. There's also lots of evidence from both my lab and others to suggest that humans, rely on internal simulation models to actually enable things that we think of as quintessentially human, things like the ability to create and use tools or construct different, large constructions. We've also done a lot of work to show that when we make the simulators that we're using differentiable, either by designing them that way or by learning and parameterizing them with neural networks, the gradients that you get can support very complex planning and high dimensional design that isn't possible without access to these gradients. So across these fields, there are sort of two axes to simulation that are key, at least in my work, and I'm going to call those broadly sort of precision and perception. So what I mean on the precision side is that, as mentioned in sort of these engineering cases, and also often in robotics.
Sorry, we had a technical problem.
Yeah.
We lost you for a second.
Oh, you lost my voice entirely. Can you?
Is it good before? Okay. Okay, the floor is yours. Sorry.
Can you hear me now? I guess someone has to either type or unmute to let me know if I can be heard.
Sorry about that. Yeah, do you mind going back 1 minute and just confirming?
Yeah, of course. Okay. You can hear me now, though?
Yes.
Okay, excellent. So here we are. Should I just start from this slide again?
That's perfect.
Okay, awesome.
You heard the top row for sure.
You heard up to the robotics part, sorry?
Yes.
Okay.
No, sorry.
And now
your first row.
The first row, perfect. I only have one line on the second row, so let's start from there. So I just wanted to say that when we make simulators differentiable, either by design, by explicitly writing their equations that way, or by learning them and parameterizing them with neural networks, we've shown that we can use their gradients to do very complex planning and high-dimensional design problems that you simply cannot do without access to those gradients. And across sort of these fields, robotics, engineering, physical reasoning, there are sort of two axes to simulation that end up being key and that are major focuses of study for people. I'm going to call these broadly precision and perception. So on the precision side, simulators often need to be precise. Having a simulator that incorrectly predicts how airflow is going to move around a wing could have pretty disastrous consequences if you're relying on this to design a wing that's going to keep an airplane in the sky. But more mundanely, some aspects of physics are actually also just very hard to model precisely. things like friction or contact, and incorrect parameterizations of these can lead to pretty incorrect predictions of seemingly simple actions, things like just pushing objects along tables. Especially in robotics, in order to actually simulate something, you also need to be able to perceive it, right? You need to get the information from your sensors into some simulatable representation. And this ends up being critical for making simulation actually useful to systems interacting with the real world, especially online. So today I'm going to talk to you about some of my work along each of these axes, specifically how we learn differentiable simulators, which are both precise and which can be derived from sensor-based input without relying on full state information. And we're going to start out by looking at precision here. So one place where precision is a particular challenge is in rigid body dynamics. Contacts in particular introduce a pretty significant challenge in that any time two rigid objects come into contact, there's a discontinuous change in their dynamics. This really nice paper from Frommer and colleagues in 2020 showed that these end-to-end models, here represented as LSTMs, really struggled to represent these sharp contact discontinuities correctly. And if you use the predictions from an LSTM, you find that the objects end up penetrating the floor. And when undergoing these bounces, they seem to show these sort of smooth transitions instead of these sharp step functions like we would expect. But there's also, yeah? Question?
Nope, you're good.
Okay, cool. However, system identification with analytic models is also not particularly accurate. It doesn't solve every problem for rigid dynamics. So for example, in this case of a cube being tossed onto a table, Drake here in blue doesn't capture the behavior of the cube in gray very well at all, despite the relative simplicity of this scenario. And this is because there are these subscale variations in the surfaces of objects that affect their movements that are almost impossible to capture correctly. So in this project that we're going to talk about first, we asked, can a different kind of neural network do better than either of these, better than these analytic models and better than these sort of LSTM-based neural networks? And that's where we're going to enter for the first time graph neural networks. Now, I'm not going to explain graph neural networks in too much detail, but the main thing you need to understand is, as their name suggests, graph neural networks are basically neural networks that operate on graphs. And a key insight that we had here was that we can represent rigid body dynamics as graphs and then use graph neural networks to learn rigid dynamics models. So how do we do that? We represent each rigid object by its mesh, which is basically just a graph made out of many triangles and the vertices that represent the different edges. This graph is then going to be passed to a graph neural network, which predicts the acceleration of each vertex in the rigid body mesh. And then we integrate those accelerations to get next time step positions for every vertex in our rigid mesh. This then lets us do a simple L2 loss on the predicted and ground truth positions of the object in order to learn the GraphNet model of rigid dynamics here. Now, a key point here is that because we're representing and learning the accelerations of each of the different object nodes here of the mesh individually, we're no longer guaranteed to have a shape that remains rigid over time. But it also means that now we're predicting how things move more locally in space. Also, if you're paying attention, you're going to notice that there's this white area here that's sort of odd, and that there's also a key missing point from how we're representing graphs to then pass to our graph neural networks, which is how do we actually represent the interactions between objects? We need to have some way for one rigid object to communicate with another rigid object such that they understand that they're in close proximity and they're going to come into contact and they should bounce away. So that's not actually a super trivial thing to do. If we do the simplest possible thing that we could imagine, and we take a very simple scenario here of just this rigid polygon interacting with this rigid cube, if we wanted to just connect the vertices or the nodes of these two objects, we would do so by looking at a little radius around each of our vertices and seeing if there's another vertex of the other object that's close enough to come into contact. And that's what's shown as a sort of red radius ball here. But for something like this cube, if something is contacting it in the middle of this face here, then a small radius is actually not going to allow you to have any edges that connect these two objects. And so they're not going to have any way of communicating with each other that they're close by. The simple thing, right, would be to just use a much larger radius here, but now you're going to have really a huge number of edges because you need to connect all of you're going to end up connecting all of the different vertices of this cube to this yellow polygon, which you don't actually need to do in order to represent the contact between them. You could also potentially use a particle model, but now you're going to have way more edges and way more nodes. And so instead, in this paper, we presented this method called face interaction graph networks, which instead connects the faces of different objects together rather than the vertices directly. And I don't have time to go into the details there, but if you're curious, I'd be happy to talk more afterwards. This face interaction representation for how we connect different rigid objects ends up allowing us to do pretty impressive rollouts of fairly complex objects interacting with each other under gravity. So this is a model that's trained on just 10 different shapes that are all thrown together onto a table. And again, we represent their meshes of each object, and then we connect them either based on their faces, that's the FigNet model shown in blue, or these alternative representations, which are shown as red, yellow, and green. And connecting at this face level ends up really dramatically improving your translation and rotation error for these complex multi-body scene interactions. Because we represent shapes with graphs, we can also generalize to new shapes that we didn't see in training. So again, here the model was trained with access to only 10 distinct shapes. You're seeing a selection of those on the left here. But it can generalize to actually thousands of shapes at test time that it's never seen before. So these are just random scanned objects on the right. And you're seeing it's doing a pretty good job of predicting how those objects move. In fact, in this case, it's doing as good a job as the ground truth simulator. So unlike other end-to-end approaches, graph networks can also learn and resolve these sort of sharp discontinuities in dynamics that are introduced by contact. It is able to track the ground truth dynamics for this cube tossing task extremely closely with ground truth in yellow and predicted in blue. And if we look at something like the Z velocity, where we expect these sort of very sharp changes that look almost like step functions, then we can see that too, with again, the blue and the orange tracking each other very nicely across a single cube toss. And we can also look at how graph neural networks compare to analytic simulators when they try to capture real world behavior. So this is still a cube tossing task, this one from Frommer et al. But now we have real trajectories of how these cubes move. And when trained on this real data, the graph network can capture the contact behavior here remarkably well. So here, the blue is the graph neural network rollout, and green is the re-rendered real cube trajectory. And you can see they match pretty closely in 3 random samples from the data set. We can also compare to analytic simulators in terms of the position and rotation error here, as well as contact nets, which is a sort of analytic learned simulation blend that's quite nice. The analytic simulators here are shown as these dashed lines, and we perform system identification for each of Majoko, Drake, and Bullet to try to match the real cube trajectory as closely as possible. But what we find is that the graph neural network actually requires relatively little data to perform just as well as these system identification techniques. For example, in rotational error, by 32 trajectories here, the graph neural network is already performing as well in predicting the rotation of the cube. And by 256 trajectories having access to, it's dramatically outperforming rotation prediction and even outperforming position prediction as well. I thought this was quite cool because it suggests that these GraphNet models can actually be better than analytic ones, even with relatively little training data, which is often not the regime we think of for neural networks anymore. You could complain to me, right? That's just a cube. What about these more complex shapes that you talked about at the beginning? And I'll show you an example of that here. So here we took a data set from Yu et al. Back in 2016, where they have a robot pushing one of 11 different shapes along one of 4 different surfaces at a variety of speeds. And here the friction is that you have 2 challenges. One is the challenge of actually converting your state information into a correct sort of simulatable representation. And the other is just that friction here is particularly hard to model. But even in this case, the graph network can learn to handle these real-world trajectories in a pretty nicely data-driven way, where the simulators dramatically outperform these analytic models, again shown as these dashed lines, with as few as about 128 trajectories, which are spread across the 11 different shapes. So that's only approximately 10 trajectories per shape-ish. And with more trajectories, this error drops pretty far down, resulting in about a 2x reduction overall. So that's all nice, right? These graph neural networks seem to work reasonably well. We can represent the interactions between objects. We can get them to do cool stuff. But if we wanted to scale them to now having to deal with extremely complicated scenes, like the ones you see here, where we're just tossing a huge number of objects onto the ground, they run out of memory because simply the graphs are too big, right? For 380 objects here on the left, you have over 1 million nodes. On the right, you have 384,000. We simply can't fit those into memory, even working at Google DeepMind. So what do we do in such cases? My colleague, Yulia Rubinova, and our team thought about replacing these mesh representations for objects with learned SDFs instead. This allows us to not need to represent the mesh of every object in the scene, but instead learn a reasonably compact multi-layer perceptron that maps the mesh into a signed distance function. A signed distance function, for those of you who don't know very quickly, is a function that tells you how far away a point is in space from the surface of an object. So it gives you basically a distance function. And we can use that to basically do a couple little changes to our graph neural networks and get some really nice scaling properties out of this model. So here, I'm showing you how the number of collision edges, the number of total edges in the graph, and then the dynamics computation time, as well as the total computation time changes as a function of the number of objects for this sort of complex example over here of these many different metal balls with this dog food bowl. And what you're seeing is that SDF Sim, which is the SDF-based simulator, ends up scaling very nicely in green without increasing too much the total number of edges, and while having lower overall time per step computation in terms of inference rollouts. It also has some other nice properties in that you can run simulations now directly on 3D reconstructions without having to do this intermediate step of marching cubes or some other algorithm to get a mesh out of a nerf. And you do suffer a very small cost to your actual accuracy, measured here in translation error. This green bar SDF Sim is a little bit higher than our face interaction GraphNet models, but it's not extreme, especially if you consider that when you have over 100 objects, it might just be extremely difficult to predict those accurately regardless. So overall for this section, I want to just summarize by saying that representing objects and collisions in these more sensible ways using graph neural networks leads to pretty big improvements, not just in our ability to simulate rigid body dynamics, but also it ends up being more accurate than system ID with analytic simulators for at least some reasonably simple real world scenes. But of course, that isn't the whole story, right? Because we rarely get such precise shapes and locations for objects in order to train these nice GraphNet simulators. Instead, what we get are these very messy visual scenes, right? Like these ones, which resemble what my kitchen looks like at the moment. And we still need to figure out how our actions are going to influence the ways in which these objects move. And there's all kinds of problems here, right? Like self-occlusion, many of these objects aren't relevant, many problems that we haven't so far touched. So in the second half of this talk, this is going to bring, and it won't be as long as the first half, so we'll move a little bit more quickly. This brings us to perception, which is how do we go from raw sensor information to having a physical simulator. So this is challenging for sort of two big reasons. The first is that we don't have a notion of object anymore. And even things like segment anything here applied to a reasonably simple-ish scene from a micro kitchen in the London DeepMind office ends up not doing a particularly good job of segmenting objects. But the second is perhaps the more fundamental problem is that we don't have correspondences anymore. That is, which particles in the previous frame correspond to which particles in the next frame. And this means we can't use our regular graph network loss functions because they depend critically on these correspondences. So to deal with these issues, we built a model called visual particle dynamics, or VPD for short. And I'm going to cover some quick background information about how this works, but it's going to be useful to sort of keep this schematic in mind. And what's important to know right now is that critically, this model makes no assumptions about object or state information. But in return, it does require access to multi-view RGB depth data to learn. Now, the first very quick bit of background I'm going to mention, for those of you who don't know it already, is about neural radiance fields, also known as NeRFs. And NeRFs basically try to train a neural network to be used as a 3D renderer for a single scene. So that is, given a location, X, Y, Z in space, and a viewing direction from a camera, the NeRF is going to try to predict the color and visual density at that 3D location. It then renders an image by casting rays through the scene from each of the cameras and accumulating the predicted radiance. Now, what's very cool about NeRF is that it turns this sort of 2D supervision problem in terms of just a collection of images and camera poses for a static scene into 3D supervision on what appears at each point in 3D space. And that's super useful and super nice. But one extremely important caveat is that these vanilla NeRFs have no representation of a scene and no ability to generalize across scenes. It's important to remember that the trained network is actually the 3D model. So we instead use point NeRF, which is a kind of interesting extension to the NeRF formula, where instead of having the model weights represent the details of a scene, point NeRF has this explicit 3D representation where instead of getting, it gets the summary of the nearby points instead of the XYZ location. So it basically relies on its neighbors, the features of its neighbors, in order to make a prediction about the visual density and color. But what this means is that it can be used across many different scenes. And so now you can take a point NeRF and generalize across scenes by just pointing its image encoder at a few views and get a point cloud instantly. This extra structure also ends up letting you get away with only a few views per scene instead of this super dense coverage that regular NeRFs often need. So with those two pieces of background, any question? No, okay. We're gonna now quickly talk about this visual particle dynamics model. So VPD is a learned 3D simulator of physical dynamics, which trains on data sets of RGBD videos. Importantly, it has this explicit particle-based 3D representation. It's going to use a graph neural network in order to do dynamics in 3D space. And then it's going to use these point NeRF representations I just mentioned to take that 3D representation and actually render it back into camera views. So now we can get an end-to-end loss. So very quickly, the first component of VPD is this encoder. And basically, given one or more RGBD images here, we're going to use a UNet on the RGB images to get feature vector Zij, and we're going to use our camera information in depth in order to figure out where that feature point is in space. If we have multiple different cameras, then we can just concatenate all of our information together. The second component is going to be this dynamics model, which we represent using this hierarchical graph network. We're here to represent motion. Because we don't have correspondences anymore, we make one graph out of 2 time steps of points, with the past and the present nodes being just represented as different node types here in both green and blue. But as you might imagine, if we take now 2 time steps, and if our particles are just coming from a very dense coverage of a scene, then we get these massive numbers of points here. This is like 2 to the 18 or something like that. And there's just no way that we can actually do graph neural network processing at the node level. So we end up using this one abstraction layer, which are these nodes shown in red, where local blue and green time step nodes speak to their local abstract node, and then all of the processing between nodes happens at this abstract level, and that then decodes back into the next time step where we then make predictions. Finally, we have this render, which works similarly to this point nerf, and just takes all of our different locations in 3D space and tries to render a scene from that. With this in place, we can condition the model on these 2 time steps, the green and blue, and then roll it out for t steps in particle space, render the images from those t steps, and then do a supervised pixel-based loss. We compare VPD to 2 major baselines, slot former and nerf die. Slot former is one that doesn't have any kind of 3D representation, but does have object-based representations. And nerf die is a 3D representation, but makes different choices from us. They use a global scene latent instead of having something like the multi-object structure that VPD kind of has a little bit through its particles. And they also do this sequential training instead, where they first train a function that goes from images to a latent space, and then simply train a latent state predictor without going all the way back to images. So it's not quite end-to-end in the same way ours is. And we looked at the comparisons between VPD, slot former, and nerf die for 3 different data sets, 2 rigid data sets, one with just a single object, and then one that has this multi-object dynamics, and then also the deformables data set, or the fun squishy objects of fun colors that we love so much. If we look at how these different models perform for these different data sets, we can see different kinds of corruptions that we don't see with the VPD. So with sequential training, where we're not doing it end-to-end, but instead separately training an encoder and then a predictor in latent space, we end up getting deformations of the cube on contact. With something like slot former that doesn't have crisp object representations in the same way, you can't reconstruct details of the object shape, like the fact that this yellow duck is actually a duck and not just a circle. And this global representation of a latent ends up failing, particularly in these multi-object dynamic scenes where it's not representing multiple objects coming into contact with each other. One of the benefits of these sort of structured nerf decoders is that we can also generate these novel views of the trajectory rollouts for free, as you can see here. So this model was only trained on 4 different views, but we can actually, at test time, provide any different cameras along any different directions and still see very nice results. Another interesting benefit of this point-based representation is that it allows us to actually do 3D-based editing. So here, in the original data set, we always had 2 objects interacting with each other and then hitting the floor. But we can actually delete the cylinder, and then we see that the pink object just falls without deforming until it hits the floor. Or you can actually delete the floor, which is extremely out of distribution, and both objects just continue to fall without deforming. So in conclusion, for VPD, we have now this 3D editable dynamic simulation that can be learned entirely from RGBD sensors without requiring object masks or correspondences. And we hope that this is going to allow in future to be able to learn more complex 3D dynamic simulators than we've been able to do in the past. So in conclusion, today I presented to you sort of some of our work along these 2 axes of simulation, both precision and perception. And of course, there are a lot of exciting open questions for this work. One that I'm particularly excited about is how precise does simulation actually need to be? And in particular, can we modulate learned simulator precision for different tasks? How can we use their gradients effectively to do things like planning and design? How do we actually make our learned simulators faster so that they're useful for real-time inference? I didn't talk about that, but I know other speakers did. And finally, how can we best combine analytic and learned simulation? So with that, I'd like to thank you all for listening, and thank you especially to the organizers for having me. It's such a joy to be here, although I wish I could be there in person. And as mentioned at the beginning, I'm starting a lab at UBC in the Vector Institute. So if you're interested, please get in touch. Thank you.
Let's take a couple questions, and Kelsey, let us know if you have a hard time hearing our question askers.
Nope, I can hear you great at the moment.
Any questions? Yes.
Can you elaborate how you do inference on the graph neural networks, whether you need to do message passing over the entire graph and conversions of that?
Yeah, it's a great question. So we do need to do message passing over the entire graph, but we don't do many steps of message passing. It's usually on the order of 2 to 3. And the critical thing is that because the graphs are connected sparsely, we don't have to have these, like there aren't a crazy number of edges to pass messages along. But when I was talking about the switch to the SDF-based simulators, part of the reasoning for that was exactly to try to reduce the amount of message passing that we actually needed to do. The sizes of the graphs end up causing out-of-memory problems if you have sufficiently large scenes.
Yes.
So you compared the learned model to the simulators in terms of accuracy. What happens if you compare in terms of speed on the same number of cores?
Yeah, that's a great point. So for the rigid dynamics, for speed, we're definitely slower. So for the face interaction GraphNet paper that I mentioned, we compared with about 10 objects to the PyBullet simulator. And there we were between 5 and 8 times slower. So it's like really significantly slower. However, if you look at all of this for fluid simulation problems, there you can be up to 40 times faster. So it is pretty domain dependent where you get speed benefits and not. And that's why I did mention at the end that a major point, at least for the rigid body versions of these, is to improve their speed because they are slower.
All right, let's give maybe time for one more.
Yeah, just a quick question. How robust your model is to like depth artifacts, because depths can be quite noisy.
Yeah, it's also a great question. So we did an experiment with that last model where instead of using ground truth depth, we used predicted depth, and that ended up working pretty much as well. But an important caveat of that, right, is that these systems were pretty simple. And so I would expect that as you get more complicated interactions, those depth artifacts are going to be more of a problem. There's actually a paper at CoRL from Will Whitney and Jake Varley on using an extension of this model for robotics tasks where they have bimanual manipulators that each have a camera on them, and they're trying to estimate the depth from those, like they just have 2 cameras with RGB depth sensors on the robot, but that also seems to work.
All right, great. Let's thank Kelsey one more time.